at this point, this is what my 386DX build looks like. And if I step back a little bit in time, I had been using this 386DX prototype board just to try to learn a bit about the 386DX and try to get that up and running. And as part of this build, I ended up changing around the arrangement of how I did my flash ROM. And I also wanted to add more capability for more slots, get it into more of an ATX form factor as far as just physical form factor. And then I wanted to make it easier to plug in a debugger, something where I can log the signals or look at the signals and see what's going on. Previously, I was connecting to an ISA slot plus a whole lot of wires that went over to an STM32. And that was messy. It worked. It was messy just because of all the wires. So I wanted to kind of clean that up, build it into the PCB. So that's what I've done with this. I have an upper board and a lower board. They connect together through these Eurodin connectors. And pretty much all the signals I need for a standard ISA slot or a 32-bit custom slot, I've got a couple of those, all come down here, along with signals that connect into these little debug ports. And I'm just simply using a PCI Express X4 physical connector. And I'm pulling all of the address, all the data lines, 32 address lines, 32 data lines, and then a bunch of control lines and other just miscellaneous signals. And those are coming down to these headers, or basically these PCI Express slots, and I have 4 of them. And so then I have also created these little PCBs that let me just plug into one of these slots, read 32 signals off the PCI Express connector basically, and shift them through this ribbon over to this board. And then Teensy takes that data and passes it on, formats it, and passes it on to my PC through USB serial. And I am running essentially full speed, or actually high speed USB at this point, which is nice. So I don't have any real speed limitations for what I'm doing so far on the USB, unlike my previous STM32 was limited to full speed. So I've gone from full speed to high speed, or closer to high speed, and I'm serially shifting all this data over to this board. This board does have voltage level shifters just to make sure that that shifted in data doesn't cause damage to the 33 volt Teensy. But these little connectors I'm finding are working pretty nicely. These headers really are just if I want to manually plug in things. I'm really not using them, but I have found they're handy for debugging. So when I have it plugged in, it's still pretty easy to touch the scope to one of these pins and get a value that's coming up through that PCI Express connector. So I'm going to go ahead and plug this back in. I'm going to go ahead and maybe pull up this little debugger code that's running on this Teensy real quick just to show you what that looks like. And so this is the application, and it's really nothing, this is definitely nothing too exciting or too complicated, but essentially I'm just defining which pins on the Teensy I'm using for these different signals. I have some signals that I'm using to generate all of the control of those shift registers, and then I've got all these pins that there's 4 shift registers per card, so there's 16 of them, and I need to control all 16, so I'm defining which pin on the Teensy is going to receive in data from each of the shift registers. And I basically have a procedure called read serial, and if I come down here, all this is going to do is loop, and it's essentially going to read that serial, delay for 15 milliseconds, and then basically repeat. And I can adjust that value and get slightly different results, but 15 is kind of where I've got it set for now. And really all I'm doing here then is I'm not using hardware to control the shifting. I'm basically bit banging this for all practical purposes. I basically send out the control signal to all 4 that I want to shift, and I'm going to read from all 16 shift registers, and then I'll flip to the next bit, read all 16, next bit, all 16. And then as I read that, I'm putting together a 32-bit address, 32-bit data, and 32 bits for control 1 and 32 bits for control 2. And then I just simply output that through the USB serial. So if I was to pull up just from here what that looks like, you can see here it's just basically listing out. And let's see if I can make this bigger font. I don't think I can. So this is the font size. Hopefully you'll be able to get the idea here though. But as I look at this, it's reading all zeros from everything, which would make sense at this point. So I'm going to go ahead and turn on the system. And then as I turn on the system, you can see, and maybe you can kind of catch if you read the first 8 characters here, that's the address in hex. So it's trying to read this FFFC address. It's reading a bunch of zeros. And then all the rest of this is basically information about clock signal, clock 2 signal, all my ROM, RAM, enable signals, etc. And what you're seeing move a lot here would, of course, be clock 2, and clock is within this data. That's where you're seeing a bunch of that move. And the system's just doing the normal initialization at this point. And so I'm not running a super fast clock, intentionally running slowly here. But I can see it just went through the addresses I'd expect, and then it got over to my E address. So E0000 is what it jumped to, and it's running my code now, where I'm basically writing to some memory at the very beginning of RAM. And I can look at this and kind of get a feel for the fact that it looks like it's working by just having looked at that data long enough to kind of recognize what patterns I'm looking for. But I think it looks like it's working pretty well, and then it's looping back. And so all my code right now is that was in the ROM is in the RAM at address E0000. And that's essentially where my program runs. It's a small program that then does some looping, and you'll see it drop to a lower E, 0000 address, something there, work its way up, and then jump back down. And in the process, it's also going to an address that's very low in memory, that 5A, whatever it was, as it flies by. But that's all looking good. Now, if I look at voltages real quick, just a few comments here, and then I'll pull up the Windows version of this and kind of show you what I'm looking at. I have my power supply set to provide 5.10 volts. And basically that's what would be coming up here. I'm running a small little jumper over to this board. All this board is doing is providing me a clock. So if I want, I can turn down the clock, I can pause the clock, speed up the clock, or have the clock run significantly faster. I've not done any speed tests to see at what point do I have issues. So far I'm just running a clock based off of a 555 IC, so it's a slow clock at this point. And if you can pick up this LED in the video, that's just flashing at double the rate of my clock. Actually, might be double. I'd have to double check. It's either before or after I go through a flip-flop. But anyways, I think that's after the flip-flop. I'd have to go back and check the schematic. But that's showing my clock that is running. And that's what's being fed into the board, which then goes through all the rest of my system. So I've got a PSOC that does generation of the proper clock 2 and clock based on that incoming clock. Make sure that my reset signal is synchronized to that, and a bunch of other stuff. It generates the S0, S1 signals, all that. This PSOC is doing all my address decoding in general for the system, and this PSOC is used when I turn on the system to copy the ROM into RAM. And then besides that, I have address latches, transceivers, all that stuff I've talked about before. But I continue to see this run. These little LEDs on these PSOCs are tied to a couple of address lines. So as long as I see them continuing to change and move, that's a good sign. That means that something's still running. I can see on the output in the serial window here, it looks like things are continuing to run fine here as I'm talking. Now, I mentioned the voltage. Now, as far as measurements, I suppose I could take updated measurements. I'll turn on my multimeter here and just get that ready to take some measurements. As far as current draw on the system, I do have that stabilized. So when I turn on the system and the current draw it's running right now are pretty much comparable. I don't see any spike in current draw like I previously saw. And I'll describe what I did to fix that. But basically right now I'm pulling 0.75 amps, so 3/4 of an amp. And it fluctuates very slightly, but it's pretty close to that consistently. Now, if I want to look at voltages real quickly, if I come way up here, somewhere close to the banana plugs, just going to do a quick read. 5.0595 or 5.06 essentially is what I'm getting up here. And so from my power supply there, I'm losing a little bit. If I go down and pick the very corner of the board down here on the lower right, 5.055 something, so that seems fine. I'm going to just take a test spot right here. 5.057. I'm going to come to the middle of the board here and just see if I've got something. Let's see, maybe I'll grab power on my ROM. And I've got 5.0393, so almost 5.04 there. So it seemed like from previous testing, whatever I was getting on this little readout on this side card was pretty much the worst case scenario what I was seeing on the board itself. So I think voltage-wise, I'm sitting fine. Now current, what I was running into, I was having this large draw when I first turned on the system. And I knew it had something to do with my shadow ROM, because I could tell my ROM wasn't getting copied to RAM correctly. And when this should have been doing that shadowing process is when I saw the high current. So I figured I had something there that was trying to throw out something onto the bus or somewhere, or there were some control signals that were incorrect. And what it did end up being is I have 4 of these latches for addresses. And on my previous build, this one over here, I had actually pulled up pin 1, which is the output enable, and ran that over to my shadow PSOC so that it could control it, making sure that my main address latches were not outputting during that initialization, because the shadow ROM instead is going to control the addressing, not what comes off the processor. So these had to be disabled. Well, I forgot to update the schematic, so these were grounded, which meant there's an active low, so they were outputting. So my processor was trying to output addressing on the bus, as was the PSOC trying to output addressing on the bus. And obviously that's not a good situation. And what I did to find that is I basically went to the clock speed for this shadow process, which normally I run at 12 megahertz. And I slowed it down to 12 hertz just so it would take a long time. Turned on the system and just really quickly used my debugger, the stuff down here, to see which signals didn't look right. But between that, my oscilloscope, I could tell the address voltages just didn't look good. And I could also tell that these 4 address latches, normally I can feel a little temperature with them, but they were getting pretty warm, and the PSOC was hot. And so I knew this, and guessing these probably is where the issue was. So I did track that back and saw that I failed to run this signal from the PSOC to the output enable. And these were going to ground and were always outputting. So while this was trying to shadow, that's where I was seeing the huge current draw, really probably coming from the PSOC. And I'm surprised I didn't damage the PSOC. So kudos to Cypress here, or Cypress, whatever it is. This little unit seems to take a lot of abuse by me and keeps on working. So that was the one change I made. Other than that, it was just double checking I had all my soldering correct on the ICs. So I had one tiny little solder bridge on 2 of the pins on one of these little cards, and I had to correct that. But other than that, things are going pretty well as far as getting all this signal over, and what you can see is outputting then again on my screen right now. Now, if I stop this, I'm going to disconnect, and so this Teensy is still going to continue running. But if I open up the Windows application that I have that goes with this, I'll just run this, and so you can kind of see what it looks like. And let me pull this over. It popped up on the other screen here. So when it pops up, I ask, am I working on my 386SX? That's my 286/386SX, or am I working on the 386DX? because I've configured it to look at the signals differently. Obviously, the DX has 32-bit address and data. The SX does not. But if I go ahead and open that up, and it opens on the other screen, so again, I'm going to drag that over. But this is what my interface looks like at the moment. I'm going to resize this a little bit, and I can connect. And basically, this is going to let me connect to this Teensy here. And I get, again, popped up on the wrong screen, but here is my prompt. I'm going to choose COM4 down here, this USB serial that is connecting to the Teensy. And I'm going to connect to that. Once I've connected to it, then I can just start showing the output. And initially, as it fills this first page full of stuff, you see it kind of hesitates a little bit. But basically, on every clock rise CLK, every time my CLK rises, I try to log an entry down here, and I get rid of duplicates. So the way I have this working, again, back to that loop, it's just constantly polling. I'm not doing interrupts or anything here that looks at the clock here. It's just constantly scanning it and sending the data over to my PC. Now the PC, the Windows app, is where I look for, has anything changed since the last set of data that came across? And I really only want to show stuff down below if it's a rise of the CLK and something has changed. And so that's essentially what I'm showing down there is that type of information. And then up top, you can see I'm trying to visualize it also. And that's why I bring all that data over constantly is, it's drawing this based on the data coming across, not drawing it only when there's a clock edge or something like that. And if I want, I can come over here to this clock, and that's why I like this debug board. I can turn it down, and I'm going to slow it down quite a bit here. And there you can see it took a little bit to catch up, but here now you see that it's stretching this out. It's showing that it's running at a slower speed. Now the reason it gets behind is because of all the processing I'm doing in this Win app, this Windows Forms app. So I've got some optimization to do here, but at this point you can see the slower clock, it just stretches it out. I didn't have to change anything. If I want, I can pause the clock, so I'll just flip it to a manual clock. And then you'll see that the clock up here will essentially stop. And I might actually just stop this and clear the results. And let me just start up a decent clock again, hit start. So there's my clock. If I flip it, I can go to flip it to a manual, and I can just pulse it. So I can just manually now, every time I press the button, flip the edge of clock 2. And then, of course, clock is based off of clock 2. It's half the speed. So, I can manually run this faster with a button, or I can run it slower. Or I can just pause it and let it sit here like it is. Or I can, again, go back to an auto clock and let it run at that speed. And again, once this screen kind of gets filled up once, then it populates. I'm suspending the drawing of the screen and doing basically a Windows API call just so that this screen can update and not have really bad flashing or scrolling, flickering type of behavior. So let me see. Okay, there it got back to where it's running and showing all this down here. But again, handy little way to kind of go through and do this. I'm going to speed it up slightly. And actually, I could speed it up a fair amount. And as I'm speeding it up, you're seeing that the duration of these is shortening, and I don't have any support in this tool to, in the user interface, stretch these or anything. It's really just pulling at a certain speed and drawing, so the faster I get, the shorter those waves will be. And so here I've turned it up quite a bit, and you can see at that point it's probably going to struggle to keep up with all the drawing of it. So I'm going to get it down to maybe right about there. I'm going to just stop and clear it and start it again. Okay, so there I'm pulling a decent log off of this. And again, I can see it's still running. And if I look at my code, there it's at address E001418-1C, whatever. There's my 5 AC that is memory that I'm writing and reading from. And then it ended up looping back around, and it's repeating this process. And if I stop this so I can see it a little bit better, I'm doing RAM writes, I'm doing RAM reads. When I do RAM writes, I can tell which RAM chips in these, this RAM 3, RAM 2 are enabled. If I come down to the RAM reads, of course the writes aren't enabled. If I get to some other RAM writes, maybe it's other RAM chips, like here it used all 4 RAM chips as it was doing a write. So it really depends on what it's writing, and that comes back to my code. I have it look for, anytime it sees this E0000 to highlight that section just so I know it got there. And also when it first turns on, I have it highlight when it starts with the, if you call it the initialization vector, basically the address that ends in FFF0. So maybe I will clear all this. I'm going to start it, and I'm going to turn off my power and turn power back on. So you can see that that went through. I can see the reset signal flipped. There I see that it's going through processor initialization. So right now, clock 2 and clock is really all you're going to see cycle for quite a few cycles. And what I normally see there is this address that you see along with 0 for data. I can see that my clock is alternating. Clock 2 I'm only showing when it rises, so this should always be filled in. If I ever am missing a clock 2, I know something went wrong. And now I can see it's getting closer when I see this behavior here, that it goes to an IO, C, and R for the MIO, DCN, WR signals. And then pretty soon I should see it reading from, instead of this FFFC at the end, FFF0. And it's going to then read where should it jump to, and that's going to be over in this E0000 address. And then the program should pick up and run from that address. So this should be getting pretty close to finish the initialization. So there's the FFF0, the 4, the 8, the C, and then I'm going to expect a jump over to my address, and there's my E0030, and then it basically got to my E0000. So that's actually the address that it jumped to, and then it's reading the 4, the 8, and basically it's working through my program at this point. And as it's doing that, I can see there's some RAM writes up here. I'm going to actually just stop this for a second. I can show more than what I have up there. So I can show if I want address and data lines too. So if I let this run, I can also watch those signals down here, just like everything else. And I do have it set so I can scroll, but I don't redraw this screen right away. So if I scroll down, without me repainting, which I'm not doing, you see this until at some point it will repaint, which I don't think I have code in there to repaint. So I can just stop it and start it real quick and fix that. And I can run a high resolution too, but for recording, I didn't want to have too small of stuff. So let me clear that and let it keep on running. So I can see I'm still in this E range, and it's running through the loop. I can see I've got RAM reads, I've got RAM writes, more RAM reads. And this seems to be looking good. I haven't thoroughly analyzed this, but the cursory review, I'm looking at the output, it seems to be looking pretty good. And I know the shadowing is working. I know the access to RAM from the processor is working. Otherwise, it wouldn't be going through this looping code that I've got going on. On the debugger, I'm finding this works really well. These cables are thin, easy, so just a small ribbon to each of these. When I don't want to be debugging, I can just pop those 4 cards out, and when I want to debug, I pop them back in. It takes 10 seconds to do that, and I don't have to worry about forgetting to reconnect a specific control signal or something like that. Also, quick commentary on the Teensy. It has been awesome to work with. So this, out of all the little debuggers I've built, this is my favorite at this point. The coding just worked. It worked as I would expect it to work. The STM32, I ran into all kinds of just weird things with the programming, things that should work, that sometimes would, sometimes wouldn't. you'd have to dig into it and realize there was something more complicated behind the scenes you had to go set for it to work right. Full port reads didn't seem to be very friendly on the STM32. So I just had a lot of issues with the STM32, and with that, I also had to take off a lot of hardware on the back of it. There's a lot of jumpers and resistors if you want to actually use all of the pins on the specific version I was using. So this has been great. Yes, I had to put a little carrier board here with these 4 levelers, but that's pretty easy. I can add a few more levelers. I have a lot more pins, so if I want to shift in a lot more stuff, I could easily double the number of I/O pins. But right now I support 128, and I'm only probably using sub 120, maybe 110 signals I have going actually to this at the moment. So I think I am now back to where I was again with the previous board with this same code running. It's just that my debugger is a much different setup now, a much better setup, a cleaner setup, easier for me to get out of the way and bring back. This clock will disappear. I'll actually have the clock get generated off of this PSOC here. So this is all going to get a little bit cleaner here as I go. And I mentioned this in previous videos, but now I think the next step, what I'm going to get into, is I need to install a VIA here and see if I can get that VIA to work. And if I can, I'm going to communicate with this little Arduino Nano here. And this is going to let me do serial debugging, or output at least, from my processor or the system, and send serial data over to my PC. Really, it's a terminal out is what it is, the way I'm using it. And that, I'll always have there even when the debugger's not hooked up, and this is going to let me send, strings and messages and stuff like that out through that Nano. And if I can get a VIA working, then that's an even better sign. Now I've got some I/O work and I/O address decoding. Maybe some stuff's a little bit different on the 386DX. As far as address spaces, things like that. So I've got a little bit of work to do on that. But that'll probably be the next video in this specific 386DX series. I might also get one of these ISA slots populated and try to get a video card working. I think those are probably my next 2 things. So VIA with a Nano, and then an actual ISA slot with a video card, my homebrew ISA video card. My 640 by 480 card. So I think those are the next things I can do. But through all this, my program continues to be running, so that's all a good indicator to me that I think things are working pretty well. So not a gigantic update here, but I did want to just mention, again, recap. I had output enables that were supposed to be off, so I had to fix that. And I got all this debug stuff set up along with my upper lower boards working together, and all that seems good. And if I don't feel anything warm, so I think things are going well. Good enough for now. Thanks for watching. If you've got thoughts, comments, suggestions, questions, throw them below, and I'll do my best to respond. Thanks.